Welcome to this talk on subrank and optimal reduction of scalar multiplications to generic tensors. This is based on a paper by Harm Derksen, Visu Makam, and myself, Jeroen Zuiddam. We solve a problem in algebraic complexity theory about a notion called the subrank of tensors. This subrank was introduced by Strassen in 1987 to study fast matrix multiplication algorithms in computer science, and has connections to several problems in mathematics and physics. Our result is that we determine this notion, this subrank for random tensors, or equivalently almost all tensors, or sometimes people say generic tensors. And with this result, we improve on previous bounds by Strassen and Burgesser from 1991. So before going into the details of this result and some details on the proofs, let me give a quick overview. So I'm going to talk about subrank and applications first. Then I want to discuss tensor parameters more generally and their value on random tensors. Third, I will talk about the subrank of random tensors, or almost all tensors, which is our main result. Then in the fourth section, I will talk about the upper bound, then in the fifth about the lower bound. And finally, I will say something about an ingredient for the lower bound part of the proof, which is an interesting notion of a tensor space decomposition that we use and that we prove. All right, so let's get started with this notion of subrank. So I want to define for you what it is, but I'm going to start with a simpler situation. So let's talk about matrices first. So I want to talk about the rank of a matrix. So there are two characterizations that I want to mention of the rank of a matrix, of an n by n matrix M. And here's the first one. So the first is to think of it as think of decompositions of your matrix into simple matrices. Then you want to write your matrix as a sum of simple matrices, so these tensor products of vectors, and you want to minimize the number of summons in such a decomposition. That smallest number is the rank. Or equivalently, this will be useful later. You can write this as M equals an R by R identity matrix times appropriate matrices A and B. And another way to characterize the rank is using Gaussian elimination. So we can dually say, okay, the rank is the largest number R, such that there are matrices A and B, so that A times M times B equals the R by R identity matrix. That's what Gaussian elimination gives us. So these are two characterizations of rank, and a nice way to think about these two is that in the first characterization of rank, we are creating a matrix from the identity matrix. So I have the identity matrix and I'm multiplying from the left and from the right to create my matrix M. And in the second characterization, my goal is to create the identity matrix as large as possible from the matrix I'm given, so the matrix M. Okay, so these are like dual characterizations in a way of the matrix rank. Now, for tensors, we can do a similar thing. Let's do this. So there are two different notions of rank of a tensor that I want to mention, and they mimic these two notions for a matrix rank. So the first is the tensor rank. In the tensor rank, so we're given the tensor T, like an n by n tensor. And the tensor rank is, you can define it by minimizing the number R, such that I can write T as a sum of R so-called simple tensors, right? So these kind of products. Or equivalently, it's the smallest number R such that I can write T as this tensor product of linear operators times this special diagonal tensor. So sum over I equals 1 to R of EI tensor EI tensor EI. This is the tensor rank, has lots of applications, famously in designing fast matrix multiplication algorithms, also in circuit complexity more generally. So that's the first notion of rank. The second notion of rank that I want to mention here is the subrank. So that's our main, the main notion that we study. And this one is defined dually. So here we are given our tensor T, and we're trying to maximize this number S. So we're trying to create the largest diagonal matrix by acting with linear maps on our tensor in all three directions. And this is called the subrank. I denoted by Q of T. And also this has lots of applications, for example, in matrix multiplication, but also in additive combinatorics. And yeah, importantly, the rank, this tensor rank and the subrank are really different notions, so they're really not the same. All right. Now, so yeah, I've defined the tensor rank and the subrank, and the subrank is our main object of study. And I want to see the subrank quickly in a different way. So just to revise, so the matrix rank, we can think of, and the matrix rank, what we're trying to do is to take linear combinations of our matrix to make it a diagonal matrix. And then we're counting how many non-zero items there are on the diagonal, right? For the subrank, we take our tensor T, and we are taking linear combinations of the slices of the tensor in all three directions to create a diagonal tensor, right? And we're counting how many non-zero elements or how many ones are on the main diagonal maximal. So that's the definition. And this subrank has lots of connections to other to different areas. An important one is in complexity theory. There it characterizes the number of independent scalar multiplications that can be reduced to a bilinear map. So let me explain this briefly. So I've been talking about tensors and the subrank of a tensor, but tensors are well known to correspond one-to-one to bilinear maps. And on bilinear maps, we have a natural notion of a reduction. So if we have two bilinear maps, G and F, then we can say G reduces to F, or G is at most F, if and only if there are linear maps A, B, and C, such that for every input X and Y, G of XY equals C applied to F of A times X and B times Y. So yeah, that's a very natural notion of a reduction. And if we're given, if we have this reduction, we can phrase the subrank in terms of it. So if we're given a bilinear map F, then the subrank is the largest number n, such that Gn reduces to F, where Gn is the special bilinear map that takes vectors of length n, x and y, and it multiplies them pointwise. So it outputs x1 times y1, x2 times y2, etc. So yeah, the subrank is really the largest number of independent scalar multiplications that can be reduced to F. So that's what it means in algebraic complexity theory. There are other ways of using the subrank in other areas. In quantum information, it measures a certain type of entanglement, namely this G at Z type. And in combinatorics, the subrank can be used to upper bound the hypergraph independence number, which is an important notion for certain problems like the Kappa problem or the sunflower problem or corners. All right, so I want to talk about tensor parameters and their value on random tensors. There are lots of tensor parameters. So I have introduced to you the subrank, which we denoted by Q, and I also introduced the tensor rank, which is denoted by R. But there are many others, and there are many others that have been introduced recently and studied. The slice rank, analytic rank, geometric rank, G-stable rank. And they are ordered in a certain way. I won't go into too much detail, but roughly speaking, this is the picture. So the tensor rank is sitting between n and n squared for an n by n tensor. And the subrank is always between 0 and n. So the subrank is kind of a smaller notion. And all these other parameters are kind of sitting in this area. Now, what is there's some things are known about what happens for random tensors. So we can pick a random tensor and ask what is the value of these parameters on the random tensor. And what has been known for a long time is that the tensor rank of a random tensor is essentially maximal. So it will be n squared. And it's not very hard to see that for these other parameters in the middle over here, the value on a random tensor is n. So it's also roughly n. So it's also kind of equal to the natural upper bound on these parameters. However, for the subrank Q of t, it has been unknown what the value is on random tensors, and that's the gap we are filling here in our result. So let's get to our main result. So the subrank of random tensors. This is our theorem. For almost all tensors, almost all n by n by n tensors, or you could say random tensors, we have that the subrank is square root of n, roughly. That's our main result. So in particular, it's significantly smaller than the slice rank on a random tensor, or the analytic rank, or the geometric rank. I have a couple of remarks. So remember that almost all is kind of the same as random, is the same as generic. These are different words for the same thing. And what it means technically is that there exists a non-empty Zariski open subset U of all tensors, n by n by n tensors, such that for every tensor in this subset, we have that the subrank that the subrank is square root of n, roughly. And we give very precise bounds. So I'm stating the square root of n bound, but we have very precise bounds that are, yeah, optimal up to an additive constant, right? And this improves previous bounds. So previously, what was known was that the subrank was at most n to the power 2/3. Now we get square root n, and our result also generalizes to higher order tensors. So I'm phrasing everything for order 3 tensors, but we have it for higher order tensors too. And finally, I'd like to mention that we have a small simple application. Using our theorem, we can easily show that the subrank is not additive under the direct sum, which was also not known before. All right, so that's our result. I'd like to say some words on the methods, and I'm going to start with the upper bound. So let's get started with that. So yeah, remember that. So, okay, I'm going to introduce a new notation. So let's say that Q of n, where n is a natural number, is the subrank of a generic tensor of size n by n by n. And what we like to prove is that the subrank is at most square root of 3 times n minus 2. That's our upper bound. Okay, so roughly n, square root of n. The way we do this is that we first define this special space for every number r. We have C sub r. We define it as the set of all tensors of size n by n with subrank at least r. And then we prove 2 lemmas that together prove our upper bound. The first lemma is that the Q of n is equal to the largest number r, such that the dimension of this space C sub r equals the dimension of the full space f n n n. The dimension of full space, of course, is n cubed. That's the first lemma. And the second lemma is an upper bound on this dimension of C sub r, and this upper bound is yeah, what's written here. So n cubed minus r times r squared minus 3n plus 2. All right. Now let's see how these 2 lemmas together prove the upper bound. So let's write T for Q of n, this generic subrank. Then we have on the one hand that the dimension of C sub t must be n cubed, that's lemma 1. And on the other hand, it must be at most n cubed minus t times t squared minus 3n plus 2, that's lemma 2. If we rewrite this, what we find is that t squared minus 3n plus 2 is at most 0. And from this, it follows that t is at most the square root of 3n minus 2. So that's how you combine these lemmas to get the result. Lemma 1 is maybe intuitively like a natural lemma. I will say something briefly about lemma 2. So recall that we have this set C sub r, and lemma 2 gives this upper bound on the dimension of this variety. I'll give you the high-level ideas. So the proof idea is that we give a non-injective parametrization of the elements of C sub r. So we parameterize the elements, but in a non-unique way. We compute the dimension of the parameter space that we use, and then we subtract the dimension of what we have overcounted, like our double count, which is called fiber dimension. Technically, the way we do this is that we have this parameter space, which is called X sub R, which are precisely the tensors of size n by n by n, so for which the R by R by R subtensor has arbitrary diagonal. Okay. Then we define this map psi sub R, which is the parameterization map, which takes three matrices, three invertible matrices, and an element from the parameter space X sub R. And what it does simply is it applies these three matrices to the tensor T from X sub R. Yeah, this has image C sub R. That's not hard to see. And yeah, so this is the kind of the technical way we do this this dimension count, and yeah, we need to subtract this fiber dimension. So that's the high level proof idea. Good. So that's the upper bound. Now I want to say something about the lower bound. And the lower bound uses these same objects. So again, we have X sub R, which is this parameter space, and then psi sub R, which gives the parameterization of C sub R, but non-injectively, so with some overcount. And to prove the lower bound, I want to highlight some ideas. What you need to do, what we want to do, is find a condition that implies that the image of psi sub R has full dimension. Because as soon as you have that this image has full dimension, this image is C sub R, then you know that R is like the generic subrank. So for this, we use the notion of the differential of psi sub R. I won't go into too much detail, but there's this map called the differential. You can explicitly write it down and study it to obtain the desired lower bound. Yeah, to obtain this condition that the image has full dimension. And I won't give too much detail on this, but I want to highlight an ingredient that we use in this deduction. And this ingredient is about a special type of tensor space decompositions that's new and that we think is interesting, maybe also in other areas. So here, the goal is to write the tensor space F, the space of n by n by n tensors, as a sum of tensor subspaces as efficiently as possible in a specific way, such that each subspace has the form of an n by n matrix subspace tensored with f to the n. So what does this mean? Let me try to explain this. First, I need to introduce some notation. So suppose we're given, suppose here we have this matrix subspace X. It's a subspace of n by n matrices. Then we define X brackets 1 as the tensor subspace obtained by tensoring X with f to the n. And we tensor it with f to the n in the first, in the first leg. And similarly, we define X brackets 3 also as a tensor subspace obtained by tensoring X with f to the n, but this time we have f to the n in the third leg. So that's, I wrote it here in the third leg. And similarly, we have X bracket 2, where we take X and we tensor it with f to the n, but we put f to the n in the second leg, which is a little bit hard to write, so I didn't write it. Okay, so that's, it's 3 ways of creating a tensor subspace out of a matrix subspace. And now the theorem we prove is the following. There are subspaces, xi, x1, x2, x3, the subspaces of 3 by 3 matrices of dimension 3 each, such that the space of 3 by 3 by 3 tensors equals x1 brackets 1 plus x2 brackets 2 plus x3 brackets 3. And so this is a special kind of tensor space decomposition. You can check that the dimensions on the left-hand side that coincides with the sum of the dimensions of the spaces on the right-hand side. So this is what we mean by as efficiently as possible. Yeah, so this is an interesting tensor space decomposition that we use. And this theorem extends, so we don't only prove this, we don't only obtain a decomposition for 3 by 3 by 3 tensors, we also obtain it for tensors with local dimension n and order n. And that's actually what we need to prove our main result for k tensors instead of 3 tensors. All right. So let me finish by saying something briefly about this short application, namely that the subrank is not additive under direct sum. So here's the theorem. There are tensors S and T of size n by n by n, such that the subrank of each is at most square root of 3n minus 2, while at the same time the subrank of their direct sum is at least n. Here, direct sum means that you take these two tensors, S and T, you think of them as n by n by n blocks, and you put them next to each other with one corner touching. So you put them on the main diagonal of a bigger tensor, of a tensor size 2n by 2n by 2n. And I can briefly sketch the proof idea. So this theorem follows from our bound on our characterization of the generic subrank. And here's how it goes. What we do is we take T to be random, and we let S be equal to the n by n by n diagonal tensor with ones on the main diagonal minus T. Then again, S will be random. And so it will be random in the sense that we can apply our theorem to see that the subrank of S and also of T, because T was picked randomly, is at most square root of 3n minus 2. And on the other hand, we can see that the subrank of the direct sum of S and T is at least the subrank of their pointwise sum. That's not so hard to see. And well, the pointwise sum clearly is the identity, the n by n by n diagonal tensor, identity tensor. And that's the subrank of that tensor is kind of by definition equal to n. So that's how you prove this non-additivity result. All right, then our final slide, some selected open problems. So our upper bound is actually, our upper bound, the floor of square root 3n minus 2 is actually tight. We found that it's tight for small n, but we don't know yet whether it's always tight. It's pretty tight because it's tied up to an additive constant, but maybe this upper bound is actually the real number for all n, the real value. Second open problem is to look into these tensor space decompositions and determine all possible tensor space decompositions for different tensor formats. And finally, one interesting question is to think about what is the largest gap between the subrank of a direct sum and the sum of the subranks of these tensors. So what we show is that they can be different, but we don't know if we found the biggest gap here. All right, thanks.